So we were talking about extensive form games. We talked about transferring them. We talked about writing the strategic form game, which corresponds to an extensive form game, and using that to find Nash solutions of the extended form game. But we saw several examples. One was the entry deterrence game. The other one was the Steckelberg game, where there were Nash equilibrium. Actually, in the Steckelberg game, there were many, infinitely many of them. There were Nash equilibrium, which didn't look reasonable, okay? Which relied on, I would say, irrational behavior, non-optimization behavior of agents on certain parts of the game, which we called subgames, okay? So we will define a refinement of the Nash solution, which rules out, which eliminates such Nash solution. And the requirement, the way we'll eliminate these so-called undesirable Nash solution is by requiring that the agents behave rationally in every subgame of the game, okay? And the new solution concept we will call subgame perfect Nash solution, okay? So a strategy profile S is a subgame perfect Nash solution of the game gamma if and only if the following condition holds. For any history H of the game gamma. By the way, we'll use the word history and node interchangeably, so sometimes I might call them nodes, sometimes I might call them history. For every history, there is a corresponding single node. For every node, there's a corresponding single history. So node, a node in the tree representation of the extensive form game. For every node, there's a unique history. Every history induces corresponds to a unique node. So I'll use them interchangeably, okay? So for any history for which the part of the game that follows the history H, which we denoted with gamma H, is a subgame. For any history for which gamma H is a subgame of gamma, we have the following. The restriction of the strategy profile to the part that follows the history H, including the history H, okay? I'll tell you what I mean by that, okay? The restriction of the strategy profile S to the part of the game that follows the history H, including history H, is a Nash solution of the subgame gamma H, okay? So essentially, we're looking at the Nash solutions of every subgame. So we're requiring agents to behave rationally at every subgame of the game gamma. Not just on the overall game, but at every subgame. Okay? So let's do some examples. Let's start with the example we had, the entry deterrence game. So there we had affirmed the entrant that was planning to stay out or enter. So out, enter. If the firm firm 1 decided to stay out, the game ended. Firm 2 continued to be a monopoly on the market. If it entered, then it was firm 2's turn to take an action. It could accommodate and work under duopoly conditions, set prices, quantity, whatever, according to duopoly conditions, or get into a price war, fight. Firm 1, get into a price war. And in each case, the game ended, and the payoffs that we used were, first of all, this was the best outcome for firm 1. So there's 3 notes, so I'll start with 3. And then the second best was this outcome, the outcome corresponding to firm 1 staying out of the market. And the worst one was the outcome induced by the action of entering by firm 1 and fighting by firm 2. Okay, so that was the preferences of, that was the numeric representation of the preferences of firm 1. And for firm 2, firm 1 staying out was the best. Firm 1 entering and firm 2 accommodating was the second best, because getting into a price war, fighting firm 1, hurt it, damaged firm 1, but it also hurted firm 2 itself, so that was the worst. Okay. Okay. So rather than, so we had the histories, which the empty history, which was denoted the beginning of the game, the history denoted with the sequence O, the history denoted with the sequence E, the history denoted, which when I came here, I just realized that there's something missing there. The history where firm 1 enters and firm 2 accommodates, enters and fights. I'm sorry, I forgot something here just when I was writing, I realized. For any history H, at which an agent has to take an action, I have to add that. So it cannot be a terminal history, which is actually trivial if you take a terminal history. The subgame, the part that follows the terminal history, is just the terminal history. That's not a game. But so if we did not deal with any game which did not involve, if we would not be studying any game which included chance, this definition would have been fine. But we might be, and we will, deal with games which involves chance, so I have to add that statement too. Okay? So rather than writing histories like that, I'm just going to name them. Let me call this the history corresponding to this node, H1, H2, H3, H4, H5. Okay? So there are 2 action histories, action nodes, this one and this one, and both of them, the part following H1, well, it's the original game, so it's a subgame of the game. The portion following H3, that's this part. Again, that's a game on its own right, so that's also a subgame. So this game has 2 subgames, the game itself and the part of, and this part of the game. Those are the 2 subgames, okay? So I would like to find subgame perfect Nash solutions of this game, okay? One recommendation that I have for you is, before you attack finding the problem of finding subgame perfect Nash solutions of this game, ask yourself, what are strategies of the agents in this game, okay? That will help you see if you have made any mistakes while finding the subgame perfect Nash solution. So let's just write them. What is the strategy set of player 1? We talked about this already, right? It was, we denoted with O and E, which was the shorthand of take the action O at the history H1, at the information set, which consists of H1, take the action E at the information set, which consists of H1, okay? So it was a plan. It's not an action, it's a plan of action. And S2 is A, F, which was take the action A, that is accommodate for a tuple whose first element is from this set and second element is from this set, okay? So what do? We find the Nash solutions. So we take gamma H1, okay? And then we look at gamma H2, okay? Well, gamma H1, it's the whole game. We're going to find the Nash solutions of this game. Well, how do we find Nash solutions? We write the strategic form game corresponding to that game, to that extensive form game, which in this case has a nice, easy tabular representation, which we already did. Okay, so that was 2, 3, 2, 3. And then enter, accommodate, 3, 2. Enter, fight, 1, 1. So we find the Nash solutions of this game by finding best responses. So both of them are best response. So from here, we see that the Nash solutions of gamma H1, which is the original game, is E, A, O, F, which we already had. Then I'm going to draw gamma H. No, I'm sorry, that's not H. That should be H3. Okay. There's nothing, this is not an action history, action node. There's only 2 action nodes, action histories. So we only consider the subgame following this part and the subgame following H3. So again, that's just this game. Well, what we do is find Nash solutions, write the strategic form game corresponding to this. There's only one player, player 2, and it has 2 actions, A, F, and the payoffs are 2 and 1. Well, what is the Nash solution? If there's a single player, it just optimizes its own action. So the Nash solutions of gamma H3 is A. Okay. So our strategy profile, the subgame perfect Nash solutions, which will denote, let me add that too. Let me add that here too. The subgame perfect Nash solutions of the game gamma will denote with S for subgame, N for Nash, P for perfect, will denote the set of subgame. Will denote the set of subgame perfect Nash solutions of gamma. Okay. So the subgame perfect Nash solutions of this game, if they exist, it should be such that the restriction of the profile to this game, which there is no restriction at all, should be in this set. The restriction of the profile to this game should satisfy this condition, okay? So it should be, the only strategy profiles, the strategy profiles we have is O, A, O, F, E, A, E, F. So the only 2 strategy profiles which satisfies this condition, which is an element of this set, is EA and OF, so we rule out this. And then we look at the restriction of these strategy profiles to this subgame. Well, in this subgame, only player 2 takes an action. So it means that the restriction of this strategy profile to the subgame gamma H3 is just this. the restriction of this strategy profile to the game, the subgame gamma H3 is just this. Okay? So the restriction of this strategy profile to the game gamma H3 is not in this set, which means that we also rule out this set. The restriction, I also have to check this, the restriction of this strategy profile to the game gamma H3 is just A, which is in this set. So that's the only strategy profile which satisfies the condition, which means that the subgame perfect Nash solutions of the game gamma are the profiles E, A. Okay, that's it. So this way, by requiring that agent 2, firm 2, behaving rationally in this portion of the game, we were able to eliminate this Nash solution. Okay? So far, so good? So far, so good? Any questions? Any questions? Okay. So that's the use of the general definition. The problem with this is, well, it's not much fun to do because a game could have many subgames. Okay? Here, and then each of those subgames could have many Nash solutions. Okay? Here, that was not a big problem because it only had two subgames, and the subgames did not have that many Nash solutions. So checking this condition that the restriction of the strategy profile to the subgame be a Nash solution of the subgame was not a big problem. Okay? But in other games, that could be cumbersome. It could be many Nash solutions in the subgames, and then you have to check whether, you have to find strategy profiles which satisfies this for every subgame, which is not much fun. Okay? For example, the Steckelberg game. Okay? There are infinitely many subgames, and actually, last lecture we wrote some of the Nash solutions of the original game, and that was, again, infinitely many. Okay? And those Nash solutions were Nash solutions which were of a particular type. I could have find other Nash solutions. Okay? So using this method to find the subgame perfect Nash solutions of a Steckelberg duopoly is not much fun. Fortunately, there's an easy way out of it. Okay? So here I started from the original game and then moved to the subgames. Okay? Actually, it could have been a better idea to move backward. By definition, finding Nash solutions of simple games are simpler. Okay? So I could have started with this subgame, which is a very simple game, find the Nash solutions, and then once I find it, I could automatically rule out, okay, once I know that in this subgame, agent 2 would be playing A, would be taking the action A, I would have said, these cannot be a part of the Nash solutions, so when analyzing the original game, I wouldn't have to worry about them. Okay? I would automatically rule these out, which would leave me with a smaller game. Actually, in effect, what would happen is, well, once player 1 takes the action E, player 2 will behave rationally in this subgame, okay? And he would be playing A. So we know, and hence player 1 knows, what will happen if he takes the action E. Okay? So essentially, we could erase this part of the subgame and replace this with the payoff 3, 2. And now, this is a much simpler game to analyze. All I have to look is 2, 3, which one is bigger? 3. So player 1 at this information set will take the action E. Okay? So the basic idea is start from the simple, move upward. Rather than starting from the big, complicated game and moving downward. Okay? This method is called backward induction. Actually, it's a method that is used in finite horizon, discrete, dynamic programming. Okay? Those of you who have studied maybe industrial engineers use a similar technique in dynamic programming. Okay? That's the same idea. Let's do another example. We'll look into Stackelberg, but let's start with some finite games. Let me take it. So, left, middle, right, and then player 2 takes an action. At this case, player 3 takes an action. A, B, C, D. Okay. And here, player 3 takes an action. X, Y. Okay. And under this case, let's say player 1 takes an action again. Small l, small r. Okay. So I'm just making up a game. So let me write the numeric representation of the preferences. I'll just make up numbers. Let me write like this. Oh, I'll fit it here. Okay. So, I want to find the subgame perfect Nash solutions of this game. Okay. Again, before you attack the problem, it's a good idea to write down what the strategy sets of the players are. Again, let me label H1, H2, H3, H4, H5, H6, H7, H8, H9, H10. We labeled H11, H12. The convention usually I will use is start from the top, move down, left to right. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So what is the strategy set of player 1? What does the strategy set of player 1 consist of? Sorry? Capital L, small l. Okay? So far, so good? Okay. Again, actually, the strategy set of player 1 is a set of functions. Functions from the domain consisting of H1, that's one information set that player 1 has to take an action, and H8, that's another information set that player 2 has to take an action. So those are H8. Okay. So those are the two information sets that player 1 has to take an action. So the strategy of player 1 is a function from this set into the set of actions available to him. Okay. But these elements, capital M, capital R, can only be mapped to this information set. These actions, small l, small r, can only be mapped to this information set. So a strategy S1, for example, is okay. So this is a strategy of player one, but this is too much writing, so whenever we can, we economize on writing. So rather than writing it like a function like this, we, for example, this function, we specify with a pair. Okay? L, the first element of the pair, denotes what he will be doing in H1, and the second element of the pair tells us what he would be doing at H8. Okay? But actually, every strategy is a function. But this is a simpler representation of this function. That's another representation of a function which maps this information set to L, which maps this information set to small l. Okay? So far, so good? So, keep that in mind. So that's a shorthand notation of a function. So what is the strategy set of player two? What is the strategy set of player two? A? Oh, wait. Let me use a different. What did I? That should be. Let's make that B. A, C, A, D, B, C, B, D. Okay. And for player three, it's just X, Y. Right? So we're looking for a subgame perfect Nash solution of this game. That is, we're looking for a triple which consists of an element from this set, an element from this set, and an element from this set, if it exists. Okay? Any questions? So, how do we find the subgame perfect Nash solutions? Well, we start. So how many subgames does this game have, by the way? Okay, sorry? 5? Okay. So the part of the game which follows this node is a subgame. 1, 2, 3, 4, 5. The original game, the game itself is a subgame of itself. Okay? So as your friend said, 5. Okay? So what we'll do is we'll start with finding the Nash solutions of smaller, simpler games. So we start with information sets, histories, which any action leads to a terminal history. Yes, sir. Mm-hmm.
Like player one will always choose R because it gives higher, but when we go to H3, it will be
Okay, that way we'll look into. That's why actually I chose the numbers like that. Okay. The only thing when I was writing this game, the only thing I paid attention was those two numbers. Okay. So we start, for example, with this game. Okay. Well, that's actually not even a game. It's a one-person optimization problem. What does a rational player one do at this node? As your friend said, we'll choose R. Okay? So rather than writing the whole thing, I'm just going to put an arrow like that. Okay? Which essentially says, when you're looking for subgame perfect Nash solutions, you can rule out these cases. They cannot be a part of the subgame perfect Nash solution because the restriction of this strategy profile to this subgame is not the Nash solution of this subgame. Okay? But once we know, again, when I say we, as NL asked us, and as players, they can do the same calculation that we do. Player 2 will know that if he plays D, player 1 is going to play R, hence the resulting payoff profile is going to be 2, 1, 3. So actually, I can erase this part of the game and just keep the profile, the payoff, the numeric representation, the profile that comes from the numeric representation, 2, 1, 3. Okay? But just for the sake of completeness, let me keep this. So that was 2, 1, 3. I forgot, what did I have here? 1, 0, 1. So I'll keep the 3, so I'll put an R arrow here, and I'll put the payoff here. Okay. Now, let's look at this subgame. Actually, I rushed. Let me change this number. Let's make this 1. Otherwise, we're going to have to deal with many cases. Okay. So in this subgame, a rational player 2 will play B. So I'll put an arrow here, which would mean that player 2 will take the action B at this information set, and hence I'll move the payoff profile 3, 1, 0 up here. And then, wow, here, player 3, that's another subgame. If he takes the action X, his payoff is 0. If he takes the action Y, his payoff is 1. 1 is better than 0, so we'll take the action Y, hence we'll have 1, 1, 1 here. Okay. Now, let me look at this subgame. Well, if player 2 takes the action C, his payoff is going to be 1. If he takes the action D, his payoff is going to be 1. Okay? Which means that this part of the subgame has 2 Nash solutions. Okay? The action C, the action D. Okay? So the way we're going to deal with that is, I'll see what happens if he takes the action C, and I'll see what happens if he takes the action D. Okay? So let's start with what would happen if he takes the action D. In that case, the payoff here is going to be 2, 1, 3. So player 1 looks at his payoff. If he plays L, okay, the game will be at this history. He knows what player 2 will do, and he knows that in this case his payoff is going to be 3. If he takes the action M, the game will be at this sub-history. He knows that player 2 is indifferent between C and D. He can play C or D. So he asks, what would I do if he plays D? His payoff is going to be 2. And if he takes the action R, his payoff is going to be 4. So which one is the best? R. And that completes all the subgames. So what do we have? What do we have? As a subgame perfect Nash solution, player 1 will play R. Player 2 will play D. Okay? And player 1 will also play small r. Okay? So far, so good? So that's the subgame perfect Nash solution of this game. Okay? So far, so good? Any questions? Did I say? We should also have the action of player 3, which is? Why? We have a profile, right? A strategy for player 1, a strategy for player 2, a strategy for player 3. Should it be? B? D. Exactly, right? So the initial thing that I wrote cannot be correct. First of all, it's not a profile. A profile is a list which consists of a strategy of each player. So I should add what player 2, which strategy, which plan of action player 3 is going to use. That was why. And the other thing is, it's a profile of strategies. So this should be a strategy of player 1. It should be in this set. It is. This should be a strategy of player 2. It should be in this set. It's not. Okay? This is not a strategy. Okay? So the strategy that we have is, at this information set, player 2 takes the action B. At this information set, takes the action D. Okay? So what we have is, now this is a strategy profile. What I initially wrote was not. So it's always a good idea, once you find it, make sure that you have a profile that is a strategy of each agent, and make sure that these are actually strategies, not actions. That's why it's usually a good idea to write these out before you start solving them. Okay? D is not a strategy. It's not in here. Okay? So this is a subgame perfect Nash solution of this game. But, as your friend suggested, at this point, player 2 could have taken the action D, in which case the payoff profile would be 0, 1, 0. Again, player 1 makes the comparison. Still, R is better. So, but it means that we have another subgame perfect Nash solution, which is R, capital R, small r for player 1, BC for player 2, and Y for player 3. So the subgame perfect Nash solutions of the game gamma is the set consisting of these two strategy profiles. Okay? So far, so good? So far, so good? Any questions? Any questions? Okay. Okay, so your friend, in that case, we should have AB here. Okay, so we'll do that, but before that, okay, so this backward induction, working with the smallest games and moving upward, okay, is a very efficient way of finding subgame perfect Nash solutions. Okay, so the question of the existence of subgame perfect Nash solutions actually boils down to the existence of Nash solutions. Okay, and we have certain conditions for that, but actually we can say even more. You see, for example, what do we have here? Every history here induces a subgame. And actually, when we work this backward idea, the subgames actually are reduced to single agent problems, which is actually, existence of a Nash solution becomes equivalent to existence of a maximizer. Okay? Okay? So, if you can guarantee that at each history, at each one-person game, there is a maximizer of the payoffs of the agent involved, then we would guarantee the existence of a subgame perfect Nash solution. So here, okay, so for this game to have a subgame perfect Nash solution, this game should have a Nash solution. But that's a one-person game. Nash solution of this game is a strategy which maximizes the payoff of player 1. So if there is it's an action which maximizes the payoff of player 1. If player 1 has an action which maximizes his payoff, then this game would have a Nash solution. Okay? Well, under what conditions will that be the case? Well, for example, if the number of available actions is finite, there would be a maximizer. Okay? So if the number of actions available at this history to player 1 is finite, there will be a maximizer, maybe more than one. Okay? Then write that maximizer here. Now, so once I find the Nash solutions of this game, we know what will happen when we come to this history. So essentially, I can remove that part of the game and replace it with the payoff resulting from payoff or payoffs resulting from the optimal action of player one. Then this is essentially a one-person problem. Okay? So finding the Nash solutions of this subgame actually reduces to finding the optimal action, the maximizing action of player two in this branch, in this node, at this node. Okay? So when am I guaranteed the existence of a maximizer? Well, if the number of available actions is finite, there will definitely be a maximizer. And I can go up all the way down. Okay? So if each history can be reduced to, if the subgame following each history can be reduced to a single person optimization problem, and the number of actions available to the agent who will take an action at that history is finite, the game will have a subgame perfect Nash solution. Okay? So I'll write down those two conditions. So the first thing we had was each history, okay, should be essentially be able to reduce to each action history should essentially be reduced to a single person decision problem. That would be the case only if each information set consists of a singleton. Okay? Those are special types of game. We give a name to them. They are called perfect information game. Okay? So a game gamma is a perfect information game. And if and only if the information, if and only if information sets of each individual, each agent is a singleton. That is contains a single point, which exactly means agents do know what actions the agents that took an action before them took. Okay? Every information set consists of a singleton. So this game is a perfect information game. That's a single. That's an information set. That's another. Okay, but if we change this game as your friend suggested, putting those two nodes into the same information set, this is no longer a perfect information game. Okay, so if a game is perfect information, I can start with the action history, which leads to a terminal history. That becomes a one-person problem, and then move my way up by solving one-person problems. Okay? And we know that those one-person problems will have a solution if and only if, well, not if and only if the available actions are finite. So the theorem, every finite perfect information game has a subgame perfect Nash solution, which can be found by using this backward induction method. Okay, what do I mean by finite? Finite extensive form game is a game where the number of nodes, the number of histories is finite, which means that there should be a finite number of agents, which is always what we take, And each agent has a finite number of actions at every node that I have to take. And the game has a finite horizon. Okay? Any questions? Any questions? So we have to stop. So next Monday, we don't have a class. Next lecture, we'll look into this and other examples. Next Thursday, we will start at 9 o'clock. Okay? Monday, we don't have class. You can and you should see your exam papers, no matter what your grade is. I strongly recommend. The only problem is today and tomorrow, I'm a bit busy. Tomorrow afternoon, I might be available. I'm not sure. But today, it's quite busy. But next week, starting Wednesday, I will have more time. So my recommendation is, starting from Wednesday, do come and see your exams. Okay? No matter what your grade is, I strongly recommend that you see your papers. That's it. Have fun.